So this is an additional example for the application of the branch and bound algorithm for solving integer programming problems. And in this example, we are looking at solving this problem in which we are maximizing the objective function 7x1 plus 3x2, subject to two constraints, 2x1 plus x2 less than or equal to 9. And the second constraint, 3x1 plus 2x2 less than or equal to 13. Our decision variables are x1 and x2. They are greater or equal to 0, so they're positive, and also they're integer, so they're forced to be integer values. So what we are going to do is, remember, we start by solving the LP relaxation of the problem. So we are going to use the graphical method for this problem. And we are going to plot the constraints. So this is 2x1 plus x2. And this one is 3x1 plus 2x2, less than or equal to 13. So as you can see, for the first constraint, the one in green, that is above the other constraint. So that constraint is it's basically not making an impact in defining our feasible region because the feasible region is right there. That's the area for which both the area that always satisfies the two constraints for this problem. So that's the feasible region, the triangle in red. So, so at this point, the next step, as we have discussed in class, is to draw the isoprofit line. And if we move that isoprofit line in a parallel way in this direction, then we should be able to find the optimal solution for this problem, which is that point, that corner point right there. And the optimal solution is x1 equals 13/3, x2 equals 0. So as I mentioned already, this is the LP relaxation solution, and it's not an integer solution for the problem. So we want to find an integer solution now. So the only decision variable that is showing fractional values are 13/3. That's the fractional value. And we want to branch for x1 because x2 is already an integer. So if we set up our first node of the tree, then we have z equals 91/3. That's the optimal solution with the decision variables x1 equals 13/3 and x2 equals 0. So we are going to branch for x1. So the two integers that are closer to x1 equals 13/3 are x1 less than or equal to 4 and x1 greater or equal to 5. So we are going to branch for both of those. And if we add those two constraints to the problem, this is how the problem looks like. So this is x1 less than or equal to 4, and this is x1 greater or equal to 5. As you can see, this area is not part of the feasible region. So there will be no solution for that subproblem. In this case, x4 is limiting the feasible region. So we are cutting a piece of it. And this is our subproblem. So as I mentioned, subproblem number 3 is infeasible because it's not cutting the feasible region. So we have to solve now this other piece. So again, using the isoprofit line, we can find that this point right here, x1 equals 4, x2 equals 1/2. This point will be the optimal solution. So we still have a fractional solution for this problem. So we have to branch again. for x2 equal to 0.5. The integer solutions that are closer to it are x2 less than or equal to 0, x2 greater or equal to 1. So if we set up those two constraints, then we have this area defining a subproblem. And then we have also this line. Those are two subproblems. This line right here that is cut by x2 less than or equal to 0. And then we also have this area right here for the other subproblem. So if we solve subproblem number 4 using that isoprophet line, that would be this point right here. X1 equals 4, x2 equals 0. So that is an integer value. So that solution is integer, x1 equals 4, x2 equals 0. So that is a candidate solution. And if we find the solution for the other subproblem, the optimal solution will happen here. Again, this is using the isoprophet line. So that will be the last point touched by that line. And that solution is x1 equals 11 over 3, x2 equals 1. So at this point, we notice that we are not done, right? This is a fractional value. However, if you look at the solution for z right here, we get z equals 86 over 3. And if we look at that number, that is 86 over 3. So let me do that math. 86 over 3. That's 28.666. So 86 over 3 is 28.667. So what that means is if you were to branch on this node and find an integer solution, the best that you will be able to do is 28, okay? Which is equal to the solution that you already found. So there's no purpose for you to search for another solution to get a 28 because you already found one. So at this point, we have said, we can conclude saying that we have found an optimal solution with an integer solution, and the objective function value will be 28. Okay, so again, we don't branch anymore in this node because if you look at the objective function, that is equal to 28.667. So if you were to branch to find an optimal solution that is integer, the best that you will be able to do will be 28. And you already found a solution that is equal to 28. So there's no purpose for you to continue searching for a solution because you are not going to be able to find a better solution than the one that you already found. So this is the optimal solution for this problem.